And good morning, everyone. So yeah, I'll give you a brief overview of Aurora as from a system architecture standpoint, and then answer any question that you might have. So first of all, right, why are we building such a machine? And the answer is simple: is we want to advance various areas of technical computing and science. If you go actually on the Argon webpage, you will see links to all these various examples of research, right, from clean fusion to next generation aerospace to cancer research and the likes. There's actually some very interesting videos that you can see. But so in order to solve these complex problems, we do need machines that actually are getting to the next generation of performance. So a couple of fun facts first before we go into the technical details. What you can see here is the first row of Aurora. Aurora is fully installed with its final hardware configuration on the floor, and we're currently working at reaching scale to make it available later this year. So it's an exascale machine. What does that mean? It means that it's going to take it about a second to solve math problems that would take all of us, 40 years as a humanity. Aurora it weighs 600 tons total. All these cabinets and the hardware and the liquid cooling that comes with it. It's about the size of one of the largest airplanes ever built, the A380. The number of cables, optical cables that are connecting all the racks, right, through its high-end fabric, is 300 miles. So again, it's quite a long distance, equivalent to Boston to Montreal. The floor space, again, right, as you can see on the picture, right, the full floor space that's used on Aurora, which is multiple rows of what you see on the picture, is roughly 10,000 square feet. So again, about 4 tennis courts. The storage, and again, I'll talk a little bit about it. The storage solution that we have on Aurora, fast storage solution, is able in 8 minutes to store enough characters that if we were to write them in books, we could actually reach from Earth to the moon. So again, quite massive numbers there that give perspective to the size of the machine. And as I was mentioning, right, from a storage perspective, we have 230 petabytes of available on-network high-speed storage, which is about 70 years of high-definition video. So again, right, a machine of that size obviously requires a system that also has impressive specs, which is what we're getting to now. So from a compute perspective, what you see at the bottom left is a picture of our blade, the compute blade. It has two CPUs that are Xeon Max CPUs, so Xeon plus HBM, and I'll have a slide on that too. With DDR memory connected to it, and then it has six GPUs, what we call our GPU Max series, and we build over 10,000 of these nodes together. Again, right, fully interconnected, which gives us more than 20,000 GPUs and 60,000. 20,000 CPUs and 60,000 GPUs together. The fabric that connects those blades together is a high-end fabric that was developed by HPE called Slingshot. Each node has 8 fabric endpoints at 25 gigabytes per second, which gives us an aggregated peak injection bandwidth across the system over 2 petabytes per second, and a bisection bandwidth using a Dragonfly topology to connect all these nodes together of 0.69 petabytes per second. Not included in those numbers is the fabric endpoints that are part of that high-end fabric that are connecting both the service nodes as well as the storage, which I'll address just later. So if you summarize 10,000 nodes with the specs of each one of our components there, you get to memory capacities and bandwidth numbers that are quite staggering. So we have over 10 petabytes of DDR capacity across the compute. We have over 1.3 petabytes of HBM CPU capacity directly attached, right, to the Xeon Xeon CPU, and we have over 8 petabytes of memory of HBM memory on the GPU. In terms of number, again, with respect to the DDR, it's DDR5 technology, and HBM it's HBM2E. So we roll that up to almost 6 petabytes per second of peak DDR bandwidth, 30 petabytes per second of peak HBM bandwidth on the CPU, and over 200 petabytes of peak bandwidth for the HBM on the GPU. As I was mentioning, the storage is known as DAOS, which is a distributed asynchronous object store that Intel developed. It's a piece of software that allows us to actually attach nodes with memory directly onto the network. That DAOS tier of storage allows us to get 230 petabytes of capacity onto the network, as well as 31 terabytes per second of bandwidth. And again, direct bandwidth that the nodes can access via the high-speed network. Now, one of the things that Aurora is built for, right? Aurora was built initially and spec to cover all three pillars of computing. So traditional HPC, which is a large simulations, data analytics, and AI. One of the things that we're working on right now is to effectively use Aurora to build the largest language model available for science. And again, we're targeting to hit over 1 trillion parameters for it. We're going to be using the foundation of Intel work in the software side for both Megatron and Deep Speed. And we're really targeting, again, having a large training to cover general text, scientific tests, scientific data, even GitHub codes to, again, facilitate research and accessibility. We expect that the training itself, again, with respect to the size of Aurora, is going to take about 100 hours on about around 4 trillion parameter. So again, right, quite impressive numbers when eventually that LLM is made available for science. A couple of early numbers. As I said, we're currently scaling the system to get to full size. We've seen some very encouraging numbers in terms of scaling, which is kind of like the curve that you see on the various graphs. I'm not going to go into details over the performance number, but again, you see that it's a machine that is very competitive, and also that has shown that between 1 and 100 nodes so far, we've had a very nice scaling. And so we do expect that scaling to continue, and again, really show that the machine is connected and very robust in terms of the extrapolation of performance that we get once it's fully available. So I have a few slides on the components themselves, right? The two main compute components. So the first one is what's referred to as the Xeon Max, which is effectively a Sapphire Rapid processor with HBM. It is effectively has four HBM2E stacks attached onto the package to the compute. So it provides 64 gigabytes of HBM to memory. Again, up to 2 gigabytes per core of accessible memory. And again, early results on HPCG show us that we can hit up to 220 gigaflops per second. Again, numbers that are quite amazing for a CPU. It is the first CPU that actually has HBM embedded with it. The memory models, there are multiple ones. On Aurora, we support both flat and cache mode, right? So flat, where effectively there's two memory regions that see both DDR and HBM as extension of each other, and then where HBM can also be used as a cache to effectively just supplement DDR and get local copies of memory. Again, I won't go into details here, but the early comparison on performance across the various workloads, across the different areas of computing, from energy, earth modeling, life and science, manufacturing, show that the addition of HBM gives to the CPU quite a large advantage in terms of performance and as well as performance per watt. Now a few slides on PVC on our GPU, so GPU Max series. Again, codename Ponte Vecchio. As you can see, the representation on the side, it's a pretty massive package. It does have multiple tile-based approach from a construction perspective. It has 8 HBM stacks. So again, HBM2E as well. It effectively therefore supports up to 128 megabytes of embedded memory onto the package. It is built of 128 what we call XE cores, which is effectively a mix of data types across the various opportunities that we have. On the Aurora part, it provides up to 31.5 teraflops of peak floating point double precision throughput performance. And then effectively it has also direct connection between GPUs, so which we want to call XE links. It has 16 XE links per tile, and again offers up to 976 gigabytes of GPU to GPU direct communication peak between GPUs. The configuration on Aurora, right, as I mentioned earlier, right, is 6 of the GPUs, so it is a prorated number versus to that peak, which is the absolute. So again, more on the various levels of storage and memory, sorry, of memory that and caches that we have on the part. As I mentioned, 128 gigabytes of HBM2E across 8 stacks. We also have a local L2 cache, which we call Rambo for random access memory, bandwidth optimized, which has 408 megabytes on the Aurora version of Ponte Vecchio, as well as 64 megabytes of L1 cache, right? So again, a deep hierarchy of memory and capacity with high bandwidth. From a compute perspective, right? So the XE cores, this is again the ops per clocks per core. And again, you see the various data types there, right? We have the same number of vector flops for both FP32 and FP64, and then twice as many for FP16. And then in matrix, we do have again larger numbers as usually expected, and then an expected scaling also from 2000 TF32 to 4000 bfloat 16 and floating point 16, as well as 8000 in 8s. And again, right, all these are per clock, therefore scaled with respect to the Aurora SKU that I mentioned before. We also have some ray tracing hardware capabilities on Ponte Vecchio. Again, there's 128 ray tracing units, which again are effectively providing a nice way of visualizing the data once the compute is done. It's using a number of software releases that Intel has provided early this year, both Osprey and MB4. And also it has a large number of VRAM, which is effectively very useful for again large HPC visualization. This was my last slide. I'll open it now for Q&A.
Thanks, Olivier. We had a couple of questions, and I guess we've been discussing that over chat, but I can read over them. So
Yes.
just as a note, these slides and recordings will become available
Yes.
not right after the talk, but a little bit after the talk, and we'll send an email to everyone who registered so they will know it. So the first question was related to the cooling system of the Aurora, which I mentioned it's the water-based cooling, but they would like to know how much energy is used and how much heat is created, and like yeah.
Okay. So Aurora is fully liquid cooled, right? For the compute part, not the non-compute. So there's absolutely no fans. And let me actually maybe go back to one of the slides where I can talk about it a bit. For the specificity, by the way, of the energy that is consumed in order to to provide the cooling, I would frankly ask you to reference Argon ALCF directly. There is, cooling towers that were built and that are providing the largest portion. There's also chillers that are again built outside the facility to bring that in. From a temperature perspective, we keep the temperature very constant, and we've seen actually pretty much no variation or very little variation even as we exercise the machine, which shows the robustness of the cooling. For the details, right, all the what you see here, right, on the blade itself, right, all the white pipes are effectively the cooling loops. There's 3 cooling loops for each node. One that takes care of 2 of the GPUs and the NICs at the back, right, which are those green cards that you see, and one that takes care of one that takes care of the 2 GPUs and the CPU that's aligned with them, and then one that takes care of the leftover 2 GPUs and the NIC cards. We try to obviously equalize the cooling expectations from each of them and across the 3 loops. As I said, after that, the cooling unit is effectively a virtual cooling unit, right? So there's a virtual cooling unit for every three racks, right? Each rack is 64 nodes or 64 blades. By the way, the switch blade is also liquid cooled. Again, right? The switch blade that you see in the middle of the picture there is provided by HPE. And so the loop is actually a continuous loop across the whole system. And as I said, right, for more details on the power required to actually cool, I would definitely ask directly the Aurora leadership facility for those numbers.
Thanks, Olivier. So the other question was related to how to get access. Currently, the Early Science Project and ECP Exascale Computing Project do have access to the Aurora early testbeds. And when Aurora becomes as a production machines, anyone can apply, like for the DD project or inside of this, even current inside, which I think it was closed last week. You can apply for that. But if you are still interested to get access, you can email me directly and I can reach out to the committee and ask them if this is possible or not. But it's very much case by case at this point. But then it becomes production machines, then it's public to everyone. So there are other questions in respect to the number of nodes, GPU and CPU, which Zilmin already answered. Another question is, are there benchmarks available that compare the Intel GPU and Aurora with the equivalent NVIDIA GPUs for HPC or AI applications?
Yes. There's quite a few. Actually, what I'll do, right? The presentation today was limited to 15 minutes. And this deck is actually part of a larger deck that we showed at ISC late May this year in Germany. I'll share that deck, and you'll see there's quite a lot of benchmarking numbers that again have been done in very tight collaboration with the Argon team that run those and did some comparison with other machines like Frontier or Polaris.
The other
question.
Yes,
thank you for the typo, by the way. I realized I didn't fix it in this.
Yeah, we can fix it before I send it out to everyone. So there is other question that why there is 30 petabytes per second for HBM CPU and 208 for GPU.
So this is really just the way things were built, right? So I mean, first the CPU only has, right, 4 stacks versus 8 on the GPU, and again the reason for that was the consumability and the sizing of each one of the components, right? Which obviously have different expectations, right? On the GPU side, the number of XE GPU cores allowed us to actually consume all the way to the bandwidth of 8 of the stacks. While on the CPU side, again, with respect to the right ratio between the number of cores we have on the CPU and the aggregate bandwidth that we could get from HBM2E and the capacity as well, right? As I was mentioning, right? We wanted to make sure that we had up to 2 gigabytes of memory capacity per core, which is roughly, fitting in a comfortable place for most workloads when users want to put their data set there. And so that's, the two were effectively built optimally. And then when you just roll it up, also because of the ratio, right? There's two CPUs for 6 GPUs. That's why you see the difference, right? So.
Thanks. The other question is the XE links on the Ponte Vecchio are connected with the other 5 GPUs inside one node, and how much bandwidth is going out of this node to the other GPUs on the other nodes? So
yeah, so on Aurora, we only use the XE links for scale up. We don't use them for scale out. Effectively, all the scale between nodes is done via the fabric, so via the slingshot fabric. And the 8 fabric endpoints that we have per node. So the XE is limited to six GPUs internally to each node.
Thank you. And then I guess the last question is, are these GPUs available on any cloud service like Intel Dev Cloud?
I think so, yes. I can provide probably more details on how to get there. And then
yeah, perhaps maybe a slide on like how to get access to Dev Cloud. That would be good.
Sure. Okay.
Thank you, Olivier. So I suggest attendees, if they still have more questions, please just put them in the chat, and maybe Olivier can respond to you on the chat. I think now time is for our next speaker. Zinwin, I believe it's you. Is that correct?
Yes.
Yes. Please go ahead and share your screen.
Okay, let me try to share my screen. Let me know if you can see my screen.
Yeah, it's in the, I guess, edit mode, so you may want to put it in presentation mode. Yes.
Okay, how it looks like.
Yes, it looks good. Thank you. Go ahead.
All right. So in the next probably 15 minutes, I'm going to cover oneAPI toolkit and the program models for the Aurora system. All right. All right. So this is a sort of a quick agenda for today's sort of knowledge sharing. So we're going to give you the big picture of the oneAPI software stack. Then I'm going to focus on the few new features we have put into the Intel's compiler for the C++, Fortran OpenP compiler. And of course, there's a set of new features we added to the Sickle compiler or DPC++ compiler. And we're following all those open standards for the Sickle 2020 or OpenP 5.2, plus or in the future, we're going to have a support for OpenP 6.0 specification. Okay. So our goal is to try to build a stronger ecosystem and deliver the leadership performance for the Aurora system. All right, let's take a quick look of the big picture of the Intel oneAPI software stack. So we have this software contract, and it's built on, there's a lot of applications you guys have been working on, AI, HPC application series, and also I know, for example, the Oak Ridge Lab or Sandia Lab has building the COCO's framework, and Livermore Lawrence Lab and Argon National Lab, you guys have been working together, build all the backend for all kinds of the framework to make sure that a lot of application runs independent of the vendor's hardware. You can have a high level, abstraction. But all those applications and the framework can build on top of the oneAPI. So oneAPI is composed with the directly program language and library, the high performance library, and the set of the tool set, right? So all those program language like OpenP and the Sickle is built on top of the what we call the hardware abstraction layer, what we call the level 0, Intel's level 0 for the the PVC, which is latest Intel's Max GPU. And of course, this oneAPI, layer is designed for make sure we can make the Intel software stack is hardware agnostic. So under the hood, you can have the support for, x86, for GPU, for FPGA, for any other device, other vendors, hardware. So I will show you a couple of examples. We have made the Sickle program language OpenP offloading works for example, for the, the NVIDIA's GPU and the AMD's GPU as well. Okay. So if you look back at the history of the Aurora project, we started around the contract was signed around the 2019 February. Okay. At that time, even before that, Intel has a major shift from our compiler technology, from our classical compiler technology, to moving to the LVM and the Spirit-based compiler technology. The goal is to make sure we can build a stronger ecosystem to support multiple hardwares, unlock our customer from single vendor's hardware. So basically, and also, of course, we're going to follow to have a stronger support for open standards like ISO C++ standard, Fortran 2008, 2018 standard, and so on. And one of the major shift is besides focus on the CPU, the program model and the compiler optimization technology, we also started adding a whole bunch of the offloading features for both OpenP, especially with the new edition of the SYCL 2020. Or at that time, it was a SYCL, 1.2.1. So with that, after, the 4 years, starting from, as I mentioned, starting from 2019 February up to now, it's more than roughly more than 4 years now. We have a pretty reasonable and mature software stack to make sure we can running the whole bunch of applications on the Aurora system now. Besides that, also we build the what we call the compatibility tool or migration tool to help you to unlock our customer or the users from the single hardware vendors or single program language to the SYCL, which is more portable solution for all the users to work on the different vendors hardware or different hardware IP, CPU, GPU, and FPGA and so on. Okay. As of today, we have pretty good successful rate. For example, if you migrate the Cuda source code to the Sickle source code, it's roughly you can have around 90% successful. You can automatically migrate with. That's why we call it migration tool, right? It's not a 100% automatic tool. So with some assistance from the users, you can actually get your app running quickly on the Intel's GPU or H100, A100 or AMD MI205 with a SYCL programming model. Okay. All right. So there is a whole bunch of the new features for the Aurora, the software stack and the oneAPI toolkit. So start from the actually 2029 as mentioned. The number of the new additions we added since the 2023.x release started last supercomputing and time frame. So there's a declare, map, interrupter support, a whole bunch of the, asynchronized offloading. We even add more extension to support a PVC with a prefetch, support a multi-GPU, multi-tile, and we also provide a pretty decent optimization report for you to show exactly to tell the customers or users to say what kind of compiler transformation has been done. And, if there's something you can look into, then continue to identify new headroom and improve the performance. Okay. So this is a focus on the OpenP new features. I'm not going to the details because of the amount of time and limitation we have. And of course, we support just-in-time combination, ahead-of-time combination for, and the new Xeon CPU and the Xe GPU. Okay. And in terms of the conformance to the standard for the OpenP 5.2 specification, at this point, we are roughly at the 93% future completion. If you attended the ECP or, there's the bird of the further the OpenP panel. So basically you can see Intel compiler is probably in the leading position in terms of supporting the 5.2 specification respect to other new features. Okay. And of course our continuous effort is try to fully standard conforming and continue to improve the performance for the SPR, Suffer Rapid and the PVC. Okay. And this is a quick chart about Intel's latest, the C++ DPC plus SYCL compiler versus Intel's classical C++ compiler, and latest LVM, client LVM client compiler and the GCC, and versus also we include the MD's LCC compiler with respect to spec performance. You can see the latest the LVM based Intel compiler beating our own classical compiler, and of course we have a leadership position versus all the GCC and the community LVM and the MD's compiler. Okay. This is another, the FP, C++ FP rate floating point. That the previous slide shows the integers rate. This is the FP's rate. So same story. We are the latest Intel compiler delivers the best performance. Okay. And there's a few things I want to highlight with this, PVC enhanced compiler support. First, in order to get improve the the memory bandwidth usage and also we add this prefetch extension as part of the OpenP standard, because OpenP allows you adding the when the specific extensions. We added the asynchronous offloading. We added all those support to deal with device pointer, device address to make sure user can do the more efficient data transformation. And of course, one of the major efforts that we did in the 2023.x release enabled ahead of time combination and the parallel build, so you can build a large HPC and AI applications for Aurora system. Of course, we added a whole bunch of the compiler support for the tools. For example, Intel's advisor tools to make sure user can use Intel's advisor tools to get offloading profitability analysis. Okay. And as you say, as I mentioned before, Sickle was one of the language. James will talk more on the Sickle. So basically, our goal is to make sure our compiler and runtime technology to support the Sickle and have multiple backend to make sure Sickle is really the language and the program model can run in everywhere. For example, it can run on the NL's Polaris. It also runs and the ASIC system, and of course it can run in the frontiers, because we have the heap backend as well. Okay, so basically this is our goal, to make sure we follow the standard and make the program model and the language runs everywhere. Okay. And as I already mentioned, we have been putting a lot of effort to make sure the Intel's the SYCL and the DP++ compiler is conformance to SYCL 2020. So SYCL 2020, there's a whole bunch of new features. This is a sort of small set of the feature I listed here. So basically, we try to implement it in the latest Intel's, for example, 2020. 3.2 released, and by end of this year, our goal is try to get close to 100 SYCL 2020 standard conformance. Okay, and there's extra extensions we add to our compiler and the runtime. For example, this is what we call the device global, which is not part of the SYCL 2020. And the reason we added this extension, because this is requested by Coco's framework. So we made a lot of effort to support all those frameworks. So make sure any application is built on top of the Coco's or Rogers can basically work with the SYCL backend. Okay. Besides, enable all those applications and hardwares, also we have been working with the community and the kernels working group to make sure we have a decent set of the testing and to test all the features introduced in the SYCL 2020. So Intel has made a huge investment and also worked closely with the community to develop this work called the SYCL conformance test suite for the SYCL 2020. So our goal for Intel's compiler is by end of the 2023, we should have all those conformance test suite 100 getting the 100% pass rate. Okay. Then this is a simple example. So basically, this XGC is used the Cuckoo's, and the Cuckoo's is building on top of the SYCL. So basically, on this special application, we got roughly 1.5x higher than FOM than over the A100 as a sort of good starting point. Okay. So as someone asked, you know, do you guys have the benchmark? Actually, we did a whole bunch of the benchmarking. For example, this is our one of the we call the heterogeneous computing computer performance benchmarks that's collected from multiple, you know, applications. This one includes around roughly around 25 applications across a different application domain: finance, application domain, AI, application domain, HPC, application domain, plus some specific like a stream and atomic historic, those are basic micro benchmarks. So overall, GUMI on the PVC today versus the A100, we are reached about 1.6, which is aligned to one of the data Olivia has been sharing. We roughly around 1.6 with if you use a PVC against the A100. Okay, on the GUMI. Okay. And as I already mentioned, we want to make sure SYCL is can running everywhere on including the Intel's GPU, NVIDIA GPU, and the AMD's GPU. So we are going to provide some your performance indications as where we are today with respect to SYCL running on A100. So this is a small set of the benchmarking we have done. Basically, we have a SYCL version running on the A100. So the Intel's the SYCL open source Ripple compiler. And versus a native CUDA. This native CUDA is basically the well-tuned native CUDA running on the A100. So you can say, don't pick on the the individual benchmark. If you pay the attention to at the high level, you can see the SYCL performance running on the A100 is pretty much on par with the native CUDA on the A100. Okay. Same story for the SYCL running on the MI100 and versus the HIPS on the MI100. So it's also on par, more or less on par. So this is sort of our selling story about the SYCL is really the portable language for the multiple vendors hardware IP and multiple vendor specific IPs. Okay. So we have been working closely with the Aurora, Argon National Lab and the DOE, ECP, ESP, a lot of application working groups with them for more than 4 years. A lot of the performance results has been published, like a QMC pack is one of the things we have worked very closely with Argon National Lab. All those performance numbers like OpenMC performance number has been published in the various conference or in the Intel's oneAPI Dev Summit. So this is something you can, all those public performance data you can find online. Okay. And one of the key takeaways by working very closely with Argon National Lab and all of you guys, we are really building the Aurora, this X-scale system, paving the way towards a scientific advance. So you can see there's a lot of good and important scientific applications running on the Aurora today. Okay. Okay, as a quick summary, this has been really the great effort with Argon National Lab, HPE, Cree, DOE, and many partners since February 2019. And the oneAPI software stack includes the SYCL, OpenAPI offloading, compiler library, and the tools. We are really strive to support the open standard and the program model for unlocking our users from a single vendor. And basically, we want to really make sure that oneAPI software stack is really the powerful vehicle for the productivity, performance, and portability. Okay. And then basically, all Aurora teams from the DOE, Argon, Intel were really in place to help all the Aurora system, users to deliver leadership performance on the Aurora system, which is built on top of the, built with the SPI and the PVC. So let's work together to make sure we really deliver the, leadership performance. That's all I have for today. Thanks for joining.
Thank you.
Now I can take the question.
Sounds good. So we have a couple of questions. I think Olivia have answered a couple, but I'm gonna talk about the ones that it hasn't been answered. So Tarek is asking, is there an equivalent of a Cuda core on these Intel GPUs for optimal performance? Mapping the computation to the Cuda thread block grid hierarchy is important. So trying to understand the compute and memory hierarchy in the Intel GPUs. And he's asking if we can provide him some pointers.
So we do have, those kind of mapping from the Cuda to the Sickle, mapping from the, the oneAPI, how the oneAPI is mapping with respect to the thread blocks. And today on the Intel's GPU, we don't have the the new thing that introduced called the thread cluster. That's the one we don't have. Except that one, we have all mappings from the thread blocks and the WAP. Essentially, if you at a high level, the Sickle's working group mapped to the thread, the map to the thread block. Then there's the thread, there's the SMD channel mapped to the SMD thread. So we have the chart for, or actually the mapping table. If anyone need that, we can, I can provide that details and information. Yes.
Thanks.
That helps. Actually, there's Intel's GPU optimization guide, and I can provide the links that has all those information I mentioned in terms of how to optimize for Intel GPU by migrating from the Cuda to the Sickle and the oneAPI. Okay.
And there is other questions that it says asking about Fortran plus OpenACC on Intel GPUs. Is Intel working with Cray, FCN compiler, or G-Fortran flank for this?
We have open talks for HPE and Cray, but in terms of the Fortran, one of the things, so far in terms of the future completion of the 2018 or 2008, Intel Fortran is in the leadership position to support all the features, including the oneAPI offload. But HPE has been using Intel, Cray has been using Intel compiler, and Cray is part of the Intel, is Intel's partner as well, right? So we have been working together, but we are looking at the F-line like F18, but we haven't directly working on those open source Fortran compiler yet. Okay.
Thank you. Okay. Okay, there is one more question, I guess. Is one Ponte Vecchio one PCIe device, or is it two PCIe device comparable with AMD Instinct of MI250X?
So actually, if you look at the architecture design of Aurora, so basically in each node, right, we have the one PCIe. So basically, we have the PCIe linked from your host to one PVC card. So which has two tiles, which has a one PCIe. So we do support the PCIe 4 and the PCIe 5. Okay. All the access from the tile 0 to tile 1 goes through the tile 0. Okay. I don't know if the MI256 they have two PCIe links from the host to the, but that's given what they have, they don't have the tile concept in the GPU, right? So they have only one PCIe link, so which is the same as the Intel. So we have the one PCIe link to the one PVC card. Okay. And also we have all the topologic, how the XE links, how PCIe links. There's we do have for the Aurora system design. I think the team of Williams' presentation has all those graphs as well at the ICS 23. Yeah.
Thanks, Amy. In the interest of time, I would suggest that attendees can ask the questions in the chat, and I would like James to share his screen.
All right, thanks, guys.
Thank you.
Let me stop sharing.
Your slides look good, James. Please.
Yeah, I had to convince Zoom to unmute me. Welcome. Hi, I'm going to wrap things up by talking about another dimension of what Aurora means for all of us. We've talked a bit about the fantastic hardware and software that'll help shape the future of science, help us do extraordinary things. But there's another very interesting dimension that I associate with with this project together, and that is oneAPI and C++ with Sickle, but not necessarily them specifically, but what they represent the key here really is together we're on the forefront of helping accelerated computing move to a more open model for programming. Like a lot of new innovations, accelerated computing's been dominated by vendor-specific software to go with vendor-specific hardware, but we're seeing a real explosion of diversity here. Now, I really like to promote Hennessy and Patterson's Turing talks that they gave a few years ago about a new golden age for computer architecture. If you've not read this, I consider this must-read things, or there's videos online of them giving this talk. But what they really emphasize is that all the different factors that have come together to promote more domain-specific hardware to take us forward, and the need for software and domain-specific languages to get that. And we see an abundance of examples of this, but reading this article and looking at the evidence, the architect in me knows this is just really the beginning. And we've seen extraordinary change over time. I'm a little bit humbled by the question about power earlier, because I was one of the architects on ASCII Red, which was the first teraflop machine. The same compute power on Argon will consume less power than a light bulb did that I would have used to write a book with. But when we delivered the machine, it was 840 kilowatts. That was in the late 90s. We're seeing the same sort of explosion today. That the programming model on Aurora is this number of PVCs surrounding a processor and trying to get the compute power from all of those. This is really just the beginning. We're going to see more and more diversity. So the question really is, what can we do to make sure that software be open to all devices, whether they're CPUs or accelerators? And we've seen a lot of innovation in this area. That there's a lot of things to build on from Cocos. Cocos certainly goes forward. It's a very strong, important capability, high value in HPC, very C++ focused. C++ with Sickle takes us some places, some additional places, and grew out of a lot of learnings, not only from Cocos, but from OpenCL. And oneAPI builds on that. The way I like to say oneAPI's complement to Sickle is, hey, what about the libraries? It's even more than that, libraries and tools and tooling. But when you focus on a language a lot, it's easy to forget, hey, I need libraries, I need tools to complement that. oneAPI to me really is the complement to Sickle in terms of providing first and foremost foundational library that are equally open. And OpenMP and MPI aren't going anywhere. They're alive and well, and they share the same vision that we should design our APIs to be open. And you might ask, why is Intel doing this? Well, Intel actually has a great diversity of hardware itself, CPUs, GPUs, and FPGAs, and we've been struggling with how do we get a programming model that can span those reasonably. And then the other is Intel's offering its manufacturing in the future to everybody. So I've been in conversations with companies you would normally consider Intel competitors about manufacturing their devices, and they're excited about, well, what can we do with these open source projects that support oneAPI to make sure they support their devices as well. So this is really an exciting place. Now, I'll complain a little about Intel marketing, because Intel marketing got so excited about the vision of supporting all hardware oneAPI that they branded our products, our software products, that at the same time as they had this open initiative. So, you'll hear oneAPI tools from Intel, and then you'll also hear oneAPI, this open spec. I don't think that will stay that way forever. I think we need to get those separated a little. Using the same word for two things is a little confusing, even though both of them share this enthusiasm. So let me go through and observe some of the things that are changing. So I put in the chat, by the way, we're working on the second edition of our Sickle book. I just sent it to the publisher last week. I figured, hey, I haven't given out a link to anyone external. Why not give it out to this group today? If you want to, you can look at the uncorrected proof. Please switch to the real book when it comes out in a few months. It'll be free PDF as well. But if you want to take a peek, and horror of horrors, if you find any typos or anything, please send me an email and let me know. There's always one more error in any book, but I think it's in really good shape. It may have some information we didn't have in the first edition. But Sickle really just does three things. It says, how do I find what devices are on the system? How do I share data with them? And how do I, share computation? How do I offload computation to them? And it does that in a C++ context, which means defining kernels. It means doing error handling, all of those things. And that's why, we actually can write a book about all that. But it's really fundamentally about, I want my program to be able to find any device hooked to the system, and I want to be able to share data and share computation. And Eric Lindell wrote a foreword for us, and he's working, he's working on Grow Max. And I think all of our applications eventually will just wake up and say, what are all the devices I could run on? I want to divide my workload across all of them. Eric demonstrated to us last fall an implication of that. He took a machine and plugged a NVIDIA GPU card in it and Intel GPU card in it, and he had a CPU with AVX512. It woke up and Sickle told him that all three of them could run his program. And he just, in his loop, he just divided up the workload across the computation, and it ran on all three. So it ran faster than if he had offloaded it just to the NVIDIA card or just to the Intel card or just AVX512. It ran on all of them. There's a great demonstration of what we're after. You may not have a machine like that has, cards from multiple GPUs plugged in, but it demonstrates the strength of it being able to adjust to the hardware. And I think all of our applications will grow to that. And LLVM is a fantastic world to work in. Shenmin mentioned that our compilers have moved to LLVM. And the beauty of this is we can say, hey, we produce wonderful code for NVIDIA. And you might say, well, how the heck do you do that? Or we produce good code, we can produce good code for ARM. The thing is, we aren't doing the production. The compiler world has already built optimal backends for these different targets. And by plugging into that world, you can start to have compilers that can produce code for multiple vendors by just directing it to backends. I don't need to write an ARM backend. You don't want me writing an ARM backend. I work at Intel. I'm not an ARM expert as much as I know way too much about x86. So let me be involved in the x86 and let someone else be involved in ARM, but let the compiler technology access both. And this is incredibly important when we see one machine have multiple architectures on it. We really need our compiler to be able to do all of these. So this is really exciting. This is new. This isn't something we could have done 10 years ago. And we envision getting the same thing going on with the libraries. You don't really want me writing a BLAS routine to run on NVIDIA or a BLAS to run on AMD, but AMD has their HIP BLAS, and Cuda, NVIDIA has cuBLAS, and Intel has MKL. So what if we get the interfaces to efficiently dispatch to those? And I'm not talking about adding overhead. I'm talking about workup interfaces, and we're getting there, and it's a very active discussion how to do that best. And we've got some stuff working for BLAS and FFTs and even DNNs now to do this vision. Because again, if you go back to that GrowMax example, the one application was dispatching some work to an NVIDIA card, some to an Intel, and some to an Intel AVX512. And you really want the best math library for each active in the exact same program. So this can't be solved by just linking in a different library. Say, oh, link in cuBLAS if you want NVIDIA. Well, what the heck about MKL? I didn't link in MKL, but or vice versa. So we really need them all to be available at the same time. And runtimes are the same way. AMD writes a nice runtime for HIP, NVIDIA has got its Cuda runtime. We're really looking at making sure that all of our decisions at how things like Sickle run is that they're able to access all the runtimes simultaneously at runtime, so that we're not picking that our application can only talk to one runtime via the linkage. So I just gave kind of a whirlwind tour because we're short on time today, but I hope I shared some of the enthusiasm and really great things that are going on, because this really is something. When we look back at the time we're in, we look back at the Aurora machine, not only are we bringing just an unprecedented amount of compute power and wonderful tooling and so forth, so the science goes forward, we are also together pushing on the idea that software should be written in such a way that it's ready for the future, regardless of what vendor produces an accelerator or what architecture it is. So another way, I might say it is, it's not just NVIDIA and it's not just GPUs. There's going to be an extraordinary variety out there, and Aurora is pushing on that, and we're getting the tools. I know when we look back in 10 years, we'll look at them and say, oh, some of that stuff was so crude, but right now it's on the forefront, and together we're figuring it out. So there's great ways to participate in this, not just to be a spectator. Huge number of the projects are open source, most of them. So there's GitHub. Just adopting and giving feedback to these things is great. This plugin support, where Intel is saying, hey, we delivered some products, but you can plug in additional support, like for AMD or NVIDIA, that Intel isn't making its tool set monolithic. Hopefully we'll see more tool sets be open so that one application can take advantage of multiple things. And then the oneAPI specification. There'll be more announcements later this year, but it's Intel's turned over management of oneAPI to an industry group. Argon's participating in this, along with a bunch of other organizations around the world. And I think they're going to announce a more formal organization later this year. And I don't even know if it'll be called oneAPI. So, stay tuned, but it's people who share this vision of where we can go. So there's lots of opportunities to participate. There's lots of people participating already. And I hope you share my enthusiasm as you work on getting your own applications to work on this Argon machine, taking a look at how we're together sort of reshaping the world to be very open to the immense amount of diversity and accelerators we're going to see in the future, and make sure that our applications are ready to seize that opportunity and use them, because that'll propel us all forward even faster. So with that, I know we passed the top of the hour, and I don't know if there were any questions, but hopefully you learned a bit about the machine, the software, and also our enthusiasm for helping encourage openness.
Thank you, James. So are there any questions for any of the speakers? If you would like, you can also unmute yourself and ask questions. Yes? Any questions? I know it has been a great discussion in the chat, and with this sort of well-received session, you may even have more deep dive to each section that we just talked today about. But if there are not more questions, I want to mention that we will be providing the recordings and the slides. Okay, I see a question now. What kind of LLVM application need to run on trillion of parameters? I don't know, what do you mean by that?
I just heard a comment early on that that Aurora can run LLM, large language models on trillions of parameters. I'm just wondering what kind of project, what kind of application we need to run that big a model.
Well, so first, it's the future. It will, right? We're trying to set that up. The plan here, right, is to effectively build an Aurora GPT infrastructure so that we can actually help researchers having access to, again, extremely large information that is scientific information, right? And as you start actually putting that data in, especially as I mentioned, right, there's been discussion about putting even GitHub repositories in there and all that, right? Obviously, well, the size just gets massive. And so we do believe that we will hit, we will need about, I would say, 2 to 4 trillion the size of the information will be about that much to get the right training to be able to have something that's actually valuable to users, right, researchers. Again, the project hasn't specifically targeted yet an application, but I mean there's, I would say, there's clear desires in terms of biology, cancer research, climate, cosmology, right? I mean the few ones that I was showing and that Jimmy was also showing in the potential applications where we think that that could enable quicker access for our researchers to actually get information in those. And as I mentioned too, if anybody's interested in collaborating on this, please let us know. We're trying to make sure that it is a community-based effort, and that it does have direct applications for the user. Right? We don't do that for stunts. We do that for science.
Thank you.
Thank you, Olivia. I see a couple more questions. So is there some sort of a network layer that allows memory access from one GPU, from one blade to another GPU memory or another blade on another blade?
Well, I mean, yeah, we right, cross node, we have RDMA like protocols or ways of transmitting data, and so, but again, it's not done in a coherent fashion, obviously, because you go through the main fabric.
Okay. The other question is, Sage is asking, this is a very vague question, but the data transfer speed from CPU memory to GPU memory is a barrier sometimes is using the GPU when compared to the fast CPU. Are there any devices being made with CPU and GPU style compute units that share the same memory?
So you're probably talking about like an XPU type configuration. So we thought about that a lot. I mean, obviously for the Aurora generation, the answer is no. We don't. The node is a discrete node with CPU and GPU separated. Again, in the future, we have been looking at those type of architecture, right? Hybrid architectures. Our next generation product, Falcon Shores, is not targeting that either. But the one after will probably be have an offering that is like that. Yes, where again the resources, not just the memory, right, but also the I/O and the likes are effectively shared between the various compute.
On the software side, we do support a unified shared memory across CPU and the GPU. And there are 3 different, memory modes you can use called the host memory, shared memory, which means based on the page migration, and the device memory is always pinned to the device. Host memory is always pinned to the host. The GPU or device can always access the host memory, but the host memory cannot access the device memory. All those stuff is part of our GPU optimization guide and the usage model, which is part of the oneAPI program model and also part of the Sickle program model to support the USM. Okay. As part of the standard. And I want to make sure people understand, for the large language model, we have been working on that for quite a bit of time. There's a lot of performance improvement has been done. We are running at like 13 billion parameters, a lot, really large, 65. There's a lot of, tuning on the performance for both SPR plus HBM and the PVC. And all those, the popular, the language, large language model, we have been running like a GPTJ, all those like proxy models and the real models as well. Okay.
Thank you, Zinmin. So there's a question with respect to Habana talk, and they have this sort of data communication layer between the 128 Habana Gaudi HBU. So I don't know what is the question. Thomas, what is the question here?
I think he's probably talking about the guided tool, yeah, which is a new, you know, the Habana's product release.
Okay. And I see that the question that is the slides will be available, and the answer yes, the slides and the recordings will be available, and we will share them on our website, and we will let you guys know. If there are no more questions, I think this was a very productive and engaging talk, and I would like to thank all of our speakers for today and attendees. And yes, we'll share the slides. And with that, thank you everyone, and I hope you have a good rest of your day.
Thank you.
Everyone.